Hello everyone. Today we will be talking about outlier detection. We know that outliers are actually an important part of any data analysis exercise that we do. Outliers can be of different types. Sometimes they may be purely mistakes in the recording of the data. In that case, we want to remove them and uh, we want to make sure that they don't affect our analysis. On the other hand, in some cases, outliers could be actually useful in detecting some hidden things in the data. Okay. And in some of the machine learning exercises, finding outliers itself may be of interest. Okay. For example, when you are dealing with uh, identifying transactions, identifying fraudulent transactions from the database of transactions, majority of the times the fraudulent transactions are actually outliers. They have either a very, in terms of amount, they can be very high, or another thing is they could be happening on inactive accounts. So if you look at the number of transactions or the duration of transaction before that, then that could be abnormally high compared to other transactions. Okay. So fraudulent transactions may be outliers in some sense, and hence when you want to solve something like a supervised learning but without using information on why, in that case outlier detection could be useful if the number of observations in one class, for example here fraud class, is very small. Okay, so we will study a couple of outlier detection methods. There are various approaches of doing outlier detection. Some approaches are what are known as global approaches, and there are some approaches which are known as local approaches. Global approaches are those which use information of all the observations in the database to determine whether an observation is an outlier or not, whereas local detection approaches are the ones where you use information about observations in some neighborhood to decide whether an observation is an outlier or not. Okay. In terms of developing methodology, there are again two approaches. Some are model-based approaches and some are purely data-driven approaches which don't require any model assumptions. So in model-based approaches, we may assume a certain distribution and then we try to find whether an observation is an outlier. For example, in multivariate analysis, you have studied Mahalanobis distance, correct? So Mahalanobis distance can be computed as distance between any observation and a population. So suppose I have a multivariate data, I have p-variate data, so I have, let me call them O1, O2, so that we don't get confused between observations and variables. So suppose O1, O2, On, these are p-variate observations, and suppose we assume that they are coming from some np, mu, sigma. Of course, mu and sigma are unknown, but we can estimate them from the data. Now, in such a scenario, what we can do? We can compute distance of each OI from this population. Okay, so we can compute first Mahalanobis distance M1 as distance of O1 from the entire population, M2 as distance of O2 from the entire population. So how do we compute MI? MI will be OI minus mu prime. If mu is known, then use mu, otherwise mu hat, sigma inverse OI minus mu. Okay, OI minus mu prime, sigma inverse OI minus mu. Okay, and now I will have M1, M2, and N. I will have N distances. What we also know is, in the case of Mahalanobis distance, that this has chi-square distribution with certain degrees of freedom. Okay, 3 degrees of freedom. if mu and sigma are known, otherwise we'll have to discount for that. So now I can compare these distances with the chi-square cutoff, and if mi is greater than corresponding chi-square cutoff of 95th percentile, okay, if mi is greater than corresponding chi-square 95th percentile, then I will declare ith observation as an outlier. Okay, then we'll declare ith observation as an outlier. So this is one of the model based approaches where we are computing distance of every observation from the population assuming normality. Okay, so normality assumption is there, and that gives me a cutoff because of the theory of multivariate normal distribution. Because we know that this is chi-square, gives me a concrete cutoff that anything which has larger value than 95th percentile of chi-square can be declared as an outlier. Okay, so this was one of the model based approaches. Let us see some data driven approaches. So two of those approaches are based on actually k nearest neighbors. Okay, so what are k nearest neighborhood based approaches? There are two approaches. One is where you decide k and check the highest distance, and one where you decide k and check the average distance. Okay, so let me call them maximum distance based approach and the next one is average distance based approach. So these are two separate approaches, but both of them are actually based on k nearest neighbor concept. Okay, so what is maximum distance based approach? For every observation, so we fix k, of course. In each of these approaches we fix k in advance. Then for every observation we record distances of the k nearest neighbor. Okay, so I will have d1, d2, dk, and this I will have for every observation. So suppose for first observation I am calling it d11, d2, d21, dk1. These are distances of k nearest neighbors for the first observation. Then similarly I will compute d12, d22, dk2. These are distances of the k nearest neighbors for the second observation, and so on. Okay, then what we will do, we will basically look at the kth distance, because kth distance is supposed to be the largest distance. These are arranged in an increasing order. So dk1 is largest among the distances in the first row, dk2 is largest among the distances in the second row, and so on. Okay, so we will have dk1, dk2, and so on, dkn. So these are distances of kth neighbors, kth nearest neighbor corresponding to every observation. We now arrange these distances and some of the large distances, so we arrange them in the increasing order. So arrange them in an ascending order, and the larger distances can then be declared as outliers. Okay, so distances which are very high out of these n distances, corresponding observations can be declared as outliers. Okay, of course there is a small problem. We don't have a strict cutoff here. So how many of them do we declare as outliers? So there are multiple ways to answer this question. We can actually see, in some sense, if there is a significant gap between some distances and other distances. Okay, so you could perhaps do clustering of these distances and see if top few distances get clustered separately. Okay, means if the clusters are not homogeneous, like one cluster has majority observations and other cluster has very few observations, then those will be extreme distances and those observations can be declared as outliers. Okay, Another approach is we resort to something like bootstrap to get significant uh, distribution of the distances under no outlier assumption, and then try to see what are more extreme distances. Okay, so these are various approaches, but still at least it gives you some sort of ranking that which observation is most likely to be an outlier. So even if you don't have a cutoff, you at least know that which observation has the highest distance, and hence it is most likely to be an outlier. Okay. Then we have average distance based approach. So where we again compute same thing. So we compute distances of the k nearest neighbors, but so d11, d21, dk1, but then we take average of these distances. So d bar 1. Similarly for second observation. So d12, d22, dk2 are distances of the k nearest neighbors of second observation. We call it d bar 2. And then rest of the procedure is same. So we rank or we arrange these average distances in an increasing order, and again see which are more extreme observations. Okay. Uh, the pros and cons of these two approaches, actually in maximum distance based it might happen that the highest distance is only creating problems, whereas others are okay. So in such cases, so this method is slightly more prone to outliers compared to average distance. Let me show you via picture. So suppose I have so you have an observation here, suppose, and you have another observation here, okay, and you have another observation here. So now here you can see that these four neighbors are pretty close, only this one is outlier. So if I am trying with k equal to 5, this observation will still be declared as outlier even though other four observations are pretty close. Compared to that, this has all the observations at a higher distance, but it may not be declared as an outlier. Okay, so to avoid such problems, we use average distance based method. Okay, so these are two approaches based on k nearest neighbors method. You also have another neighborhood based approach where what we do is we fix epsilon and pi. Okay, we fix epsilon and pi. Pi is a proportion, so pi belongs to 0, 1, and epsilon is radius, so epsilon is any positive value. Then for every observation, what we do, we check what is n epsilon oi. For every observation, we get its neighborhood. Okay, and we see how many observations are in the neighborhood of radius epsilon upon total number of observations. Okay, so let me again draw picture and we will see. So these are the observations, suppose, in which we are interested, and these are the neighbors. Okay, and suppose my epsilon for this, epsilon is common for all the observations, so epsilon is supposed such that this is a neighborhood for this observation, this is a neighborhood for this observation, and this is a neighborhood for this observation, suppose. Now you can see, let me name them. So this is suppose O1, this is O2, this is O3. Of course we have to compute it for other observations also, but as of now I am not worried about them. So for O1, out of total number of observations are how many? 5, these are 5 plus this own observation, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have total 18 observations. So for O1, this count is 5 by 18. Okay, for O2 this count is 3 by 18, and for O3 this count is 2 by 18. Okay, and we fix some pi. For example, I fix pi at 0.05. Now if 5 by 18, is it more than 0.05? Yes. So this is greater than 0.05, so this is not an outlier. 3 by 18 is 1 by 6, so this is also greater than 0.05, so this is not an outlier. 2 by 18, actually in this case, this is also greater than 0.05, so this is not an outlier. So what we will do is, we will see which neighborhoods have observations, proportion of observations less than pi. Then those will be declared as outliers. Okay, pi has to be chosen sensibly. If my pi is, if my number of observations is very high, then you don't have to worry about pi. Pi can be anything. But if number of observations is very low, then pi has to be chosen more carefully. Okay, so basically this is also again saying, checking how dense the neighborhood is. If the number of observations in the neighborhood is high, then that means that observation is not an outlier, which makes sense, right? Because it means that there are many other observations which are similar to that observation. Okay, so in that case, that is not an outlier. However, if the proportion of observations in a neighborhood is very low, then that means that there are not too many observations which are similar to this, and hence it becomes an outlier. Okay, so this is another neighborhood based approach for outlier detection. There is one more simple method which is known as deviation based approach. So the approaches that we studied so far were actually distance based approaches, and there are some deviation based approaches also. So let us see one of the deviation based approaches as a last method. Of course, there are many other methods, but right now we won't worry about them. So what are the deviation based approaches? So again, suppose we have, let me focus on univariate observations now. Okay, so I have x1, so I have x1, x2, xn as coming from some data. So these are, we assume that these are IID. We don't assume any distribution. Now we estimate variance. Generally, whenever we get data, we estimate variance, that is sigma square hat. Similarly, we can estimate sigma square hat I as variance estimate after removing ith observation. Okay, variance estimate obtained after removing ith observation. Okay, then so I will have sigma 1 hat square, sigma 2 hat square, up to sigma n hat square. Okay, now generally when you reduce the number of observations, variance should decrease, right? So we compute sigma square minus sigma I square hat, of course, for every observation. So we see how much decrease in the variance has been achieved by removing a particular observation. Okay, and if this decrease is very high, means after removing that observation, the variance has decreased drastically. Okay, so let me draw a picture. Suppose these are the observations. Okay, so this is 1, this is 2, 3, 4, 5, 6. Suppose I have a data set consisting of these 6 observations. Now, when I compute variance of all 6 and when I compute variance of these 5, variance of these 5 is going to be much smaller compared to the variance based on all 6. Okay, so this actually happens because this is an outlier. Can you see it? So this is an idea. So if this decrease is very high, then that observation will be an outlier. Again, we don't have a very strict cutoff here, but again this will give us a way of ranking the observations as outliers. Okay, so this is what is known as deviation based approach. So right now we are treating it as a univariate approach, but it could be generalized to multivariate setup. And one very simple way of generalizing it to multivariate is do this for every variable and then combine this. So take like average of this quantity across all the variables, or take sum of this quantity across all the variables and see which observation performs high. Okay, so this will be a way of converting it to uh, multivariate from the univariate setup. In fact, what we did here in the Mahalanobis distance, that can also be treated at the univariate level. So in general, if I don't want to assume normality, then one of the ways of looking at the outlierness score is through ECDF, empirical CDF. If value of empirical CDF is very high, then it means that the observation is very high. And if the value of empirical CDF is very low, then the observation is again likely to be an outlier, because the observation is towards the left extreme in the data. So people have studied ECDF based approaches also, and in ECDF based approaches, computing multivariate ECDF is not possible unless we assume some joint distribution. So what people do is they compute univariate ECDF and then assume independence, even though it is not true, we know, assume independence and simply think of joint ECDF as the product of marginal ECDF, and that gives you some sort of outlier score. Okay. Now some of you might be thinking that assumption of independence is incorrect. True, but what happens is, just like in the case of naive Bayes, if you remember, in the case of naive Bayes also we assumed independence, and still naive Bayes does give some interesting results. Similarly here also, assumption of independence may not really be very harmful. Okay, so it does give some interesting results. So these are some of the outlier detection approaches, and as I mentioned in the case of Mahalanobis distance, one other simple approach could be simply clustering the observations and seeing if you get clusters of very small size. Because if you get some clusters of very small size, then those clusters would actually be representing outliers in the data. That is another simple approach for outlier detection. Okay, so go through all these, try to work out some examples manually, and of course try to write codes for these. Okay, let me stop here.